All right, so this is a scanning electron microscope, the SEM. You don't really need to worry about this setup. Quite often when they have these types of questions, this would be a diploma question. That's a whole lot of information, but really it jumps down to the question and trying to figure out what's necessary to solve this one through. So if you look at this question, it says the electric potential difference between the electron gun and the anode that accelerates electrons to a speed of 2.65, what is the potential difference used? So we're trying to go back and remember that we're talking about turning electric potential energy over to kinetic energy. And what we're trying to do in this case is solve for that potential difference. In other words, what is that voltage acting across here? So when we solve this through rearranging the solve for V, we're left with mass times velocity squared divided by 2 times the charge. So because we're using the mass of the particle, we're talking about 9.11 times 10 to the negative 31 kilograms. We're using the speed that's given, 2.65 times 10 to the 7 meters per second. And in this case, we have 2 of these electrons. The electrons having a charge, in this case, of 1.60 times 10 to the negative 19 coulombs. When you work this through, 1/2 mv squared, just about forgot that, we're left with an answer of voltage. Let's try this out. So 9.11 times 10 to the negative 31, 9.11 to negative 31 multiplied by 2.65 times 10 to the 7 squared divided by 3.2 times 10 to the negative 19, and we end up getting roughly 2,000, or in this case 1.99999 volts. Let's go to 3 sig digs, so we're going to say 2.00 kilovolts in this case would be our voltage across these plates. Okay, so once again, we're using kinetic energy converting to electric potential. All right, it says the resolution of an electron microscope is dependent upon the de Broglie wavelength of the electron. The resolution of the SEM is about 1 nanometer, which is twice the de Broglie wavelength. So 1 nanometer is twice the de Broglie wavelength. Twice the de Broglie. So the de Broglie wavelength would be exactly half of that, 0.50 nanometers. So we're just going to write that down. Sometimes that's a little bit confusing. What is the electron speed required to produce this resolution? All right, so going back to that equation, lambda is equal to h over mv. Now we're just going to rearrange to solve for that velocity. Well, the velocity is then equal to h divided by mass times its wavelength. And if you plug these in, once again, using that 6.63 times 10 to the negative 34 joule seconds. The mass of the electron, 9.11 times 10 to the negative 31 kilograms. And then that wavelength, which is 0.50 times 10 to the negative 9 meters. And when you work this one through, so 6.63 times 10 to the negative 34 divided by 9.11 to the negative 31 divided by half, or 0.5 times 10 to the negative 9, we're left with a speed of 1.46 times 10 to the 6 meters per second. Once again, we're dealing with extremely small, extremely fast particles. All right, so try the next few questions out. A few of them are a little bit silly, talking about bullets and trying to solve for their wavelengths. Sometimes we talk about humans and humans being able to diffract. Once again, not very common. All right, so try questions 1 through 6, where number 6 is a little bit optional because we don't need to worry about so much this whole idea of the 11 degrees first order math.